All right, hello lovely humans! Welcome to part 2 of solving differential equations. Intro 2, parentheses. Okay, so in part 1, we looked at a quote-unquote simple example. Simple / straightforward for solving differential equations. Not simple necessarily, but something that we can fairly quickly kind of work through. In this episode, we're going to do 2 more examples, but these are going to be second order differential equations. One of them is going to be fairly straightforward, and then the other one, I will hint at the challenges of dealing with equations that are not necessarily separable, aka you can't nicely kind of move all of the same variables over to one side or the other. And so we're going to kind of look at a trick in differential equations that relies on using other smart people to start off your solutions from. Cool. Okay. So in this first example, we'll do something fairly straightforward in dealing with second order differential equations. Cool. Okay. So our problem statement, again from the Mathematical Methods in the Physical Sciences textbook by Mary L. Boas. This example is find the distance an object falls under Earth's gravity in t seconds if it starts at rest. I will give you another hint about differential equations again, is that whenever you are doing differential equations in a math, physics, engineering, or whatever textbook you might have, you're often going to find fairly short problems like this that pack in a lot of information. So one of the main tricks of solving differential equations is being able to read these math problem statements and pull out a lot of information from just a few amount of words. This is a really good example of that because we are talking about the distance an object falls. So that's a loaded statement in itself. There's a brief mention about gravity, but that's super key. And then this starts at rest is also super key. So the first thing is that the distance an object falls. Okay, so we know that if we're talking about physics, oftentimes in physics we use x to denote a position of an object and t to denote the time at which we're talking about the location of that object. Both of these variables matter a lot because we are dealing with space and time. We need both of them. If I were to tell you I was home, but I didn't give you a time, you'd be like, well, are you always home? No. So you have to show up at a time you know I will be home. And conversely, if I were to say, at 10 o'clock this morning, you can find me. And then you'd be like, but where? Okay, so you need both of those variables. And so in physics, we know that the velocity of a particle can be described like this, and the acceleration of a particle can be described like this. And since we're dealing with motion due to gravity, gravity is an acceleration. So we want this equation where a is actually just the constant g, where g equals 9.8 meters per second squared. So this is our starting differential equation. You can see it's second order because we have, well, a second derivative of x with respect to time. And so now we need to solve this differential equation in order to figure out the distance. I'm going to say that in very large hand quotes because we're going to end up with a variable solution, but we will get to a fairly specific solution to this problem statement. Okay, so the first thing that we need to do is to recognize that, well, this is kind of nice because g is just a constant. It's an acceleration, but our acceleration is constant. So that's nice. The other thing that I want us to note is that dx squared dt can be written like this, of d dt, dx dt. That's really what a second order derivative is. You're taking the derivative of a derivative. Same variable on the bottom. And so you actually can kind of pull out these pieces. And so you have d dt of dx dt equals g. And then what you can do is the same thing that we did in our separable solution. You multiply both sides by dt. So I'm going to erase that, g dt, and now we can integrate. So this is interesting. This is kind of a weird notation, but basically this just means a small little piece. And so what you end up with is just dx dt on this left side. And on the right side, we do the integral of a constant with respect to t, which just gives us gt, and then plus c. I should also say that there is really a constant over here too, but because it's a constant, we're gonna shove it into the constant on the right side. Okay, and now since we still have a differential equation, we're looking for an equation for x. And so we want to do the same thing we just did. We're going to multiply both sides by dt. And since there's no x over here, we don't need to do anything else. So we're going to get integral of dx equals the integral of gt plus c times dt. And so the integral of x is just going to be x, and again, kind of plus c, but we'll just shove that constant into the constant on the right side. I should say c1. And the integral of gt is 1/2 gt squared. The integral of c1 with respect to t is c1t, and then plus some other constant, which kind of shoves this constant in. Okay, so if you are familiar with physics, you'll probably recognize this equation where c1 and c2 are specific constants, specific values related to velocity and position. But if you aren't familiar with physics, that's okay, because we have enough information given where we don't have to kind of use our understanding of physics to get values for C1 and C2. So what we'll do is we will plug in our initial condition. So we know that it starts from rest. So at t equals 0, x equals 0. Oh, wait, hold on. It starts at rest. That's not position. That is velocity. Oh no, I lost my eraser. Hold on, off camera. Whoa! Okay. Okay, so the velocity equals 0. So that's actually this equation right here. So if we set this equal to 0 and set t equal to 0, we're going to get 0 equals g times 0 plus c1. So that just gives us c1 equals 0. Oh, boom! Woohoo! Party time! Okay, so that was our first initial condition. And then the second initial condition really hones in on the fact that there's not a lot of words in this, but there's a lot to read kind of between the lines, so you might say. So you also would say at t equals 0, our object hasn't fallen at all. So I kind of gave it away, but at t equals 0, x also equals 0. The object hasn't moved, it hasn't fallen, it's starting where we set the origin to be. And so we would plug that in to solve for C2. So we got 0 equals 1/2 times g 0 squared. That goes to 0. And then this has gone to 0 plus C2. So again, we get C2 equals 0. And the solution to this problem is just x equals 1/2 gt squared. So if you were given a time, let's say after 8 seconds, how far did it fall? You would just plug that in. So at t equals 8 seconds, maybe you would have this in meters. So we're going to say 1/2 g times 8 squared equals 1/2 g times 64. And that actually would give you, sorry, this is going to be seconds, my bad. So that's going to be seconds squared because we're doing an applied problem. Ha ha ha, cool. So the g has units of meter per second squared. So the second squareds are going to cancel. And you're going to get 9.8 meters times 64 times 1/2 gives you the distance that your object has traveled. I'll let you actually plug that in because I'm like a true physicist. The numbers in this case aren't of interest to me. It's the math behind the process. Cool. Okay, so that is our first example of a second order differential equation. I'm leaving out a few other key terminology pieces here. This is technically a linear equation. But I don't want to get too much into the jargon. I really want to focus on how you can handle the mathematics, and then you can apply the terminology later to really understand. The terminology is super helpful to understand what types of tools you should be using to solve the particular equation. So I think showing you some of these examples will help to kind of get that into your head. And then when you see the terminology later, you'll be like, ah, yes, okay, now I get it. Cool. Okay, so we're going to do a bit of a harder problem. Or, well, I guess I should say it's not harder necessarily, but it is different. Very different. Okay, so number 2. Okay, so given y double prime equals y with a line that passes through the origin and, oops, I should erase this. Erase. And ln of 2 comma, whoopsies, 3/4. So this and that are 2 points. So, okay, this equation, that is our differential equation. Let's assume that we're dealing with y and x. So we're going to have d squared y dx squared equals y. This is pretty weird. This is pretty challenging. And so what I'm going to say is that when we have something like this, even though it's hard to read what I wrote, let's rely on the work from past mathematicians. And so what you would find is that this is actually a really, really, really common differential equation. And so lots of people have figured out the general form, which would be y equals a e to the x plus b e to the negative x. Another solution could just be maybe y equals e to the x or y equals e to the negative x. Both of these are going to be solutions to that, or well, all 3 of these are going to be solutions to that. But I like this one, this is the one that you should start with because this is the most general form of the solution. If you start with one of the other, you might find that everything goes to 0 because maybe, for example, in one situation, maybe b goes to 0 or a goes to 0. So it's better to start with the most general form you can. And this really touches on the fact that when you're solving differential equations, very rarely are you ever going to get a single solution. You're going to get a group of solutions with certain constants that are going to kind of change depending on the nature of the problem that you are solving. So in this case, what we want to do is plug in our 2 points, 0, 0, and the natural log of 2, 3/4. So 0, 0 is a lot easier. So the first point we have, 0 equals a e to the 0, which is just 1, plus b, again, times 1. And so we end up getting a equals negative b. Not so bad. So then we plug in our second point of natural log of 2, 3/4. So xy. So we're going to get 3/4 equals a times e to the ln of 2 plus b e to the negative ln of 2. And here, actually, I want to rewrite this like this. So e to the negative x equals 1 over e to the x. So we're going to write this b over e to the ln of 2. And then we get 3/4 equals a times 2 plus b times 1/2. And here you're like, ah, now I see. Cool. And so then we just solve for a and b. We know that a equals negative b. So we get 3/4 equals negative b times 2. Or well, okay, I guess in this point I could do negative 2b plus 1/2 b. This is going to give me negative 3/2. B equals 3/4. Or a equals negative b equals 1/2. Cool. Or I guess in this case you would find b equals negative 1/2. Okay, so then you would rewrite the solution with your known constants. So you're going to get y equals 1/2, a is positive, tricky, minus 1/2 e to the negative x. This is actually one of those fancy trigonomic equations. So if you're interested in that, you can look it up. Cool. Okay. So in this case, I didn't actually solve by doing this kind of separable solution type approach. I used the fact that I already know the general form of the solution, and then I just applied my particular, I guess you could call these boundary conditions, to the problem to solve for those constants. So especially when we're doing applied mathematics, it really doesn't matter what approach you take as long as you know that the approach you're using is valid. So in this case, because we have an equation, or this equation or this equation are equivalent, because you know that lots and lots and lots of people have already solved this and figured out the general form of the solution, it's totally fine to just skip the messy details and take their solution. Because if you're trying to solve an applied problem, really the goal is to get out the important information. And all of that kind of in-between work is not necessarily going to be helpful. It's this end result that you're most interested in. So that's one of the things I love about math, is that there are always multiple solutions to get a result. And oftentimes there are perhaps more than one correct approach. But you really have to understand what you're doing so that you can make sure that you're applying the proper approach. Okay, so that was a couple of examples of second order differential equations. Again, we're dealing with ordinary differential equations, which means that there are no partial derivatives. Please let me know if you have any questions about this introduction to solving differential equations. And like I mentioned, in next week's video, we're going to dive deeper into solving some harder differential equations, and we'll also pull in some more of the terminology. Technically, we'll be doing linear differential equations, and that's where we will start to see how you solve something like this and actually work through those steps. Just in case you get a weird, funky differential equation that no one has solved before for some reason. It happens. Cool. All right. Thank you very much for watching, and we'll see you next time, lovely humans. Bye!